Okay, so then let's start the third day of the workshop. First speaker today is Daisuke Kadoh. He's living in Taiwan and speaking from National Tsinghua University. So, he's one of the rare people who are enjoying a free life without COVID now. And I hope we all can become like that and, can broadcast from our office like he's doing now. Kadoh-san, please start.
Okay, thank you. Thank you for giving me an opportunity to make the presentation. Can you see this pointer? This
Yes, white one, right?
okay,
I can
okay,
see.
okay. Today, I'd like to talk about tensor network methods in four-dimensional field theory. And actually, I propose a new tensor network tensor renormalization group method, which is applicable to any d dimension in this talk. So these tensor network methods are very effective to study the lattice model with the sign problem. So firstly, I will be explaining what the sign problem is. And in the field theory, the expectation value of an operator O is given by this multiple integral. And in the Monte Carlo method, this expectation value is approximated as an average, in a sample average over the configuration. And this configuration phi's are generated is a probability of exponential minus s. So this Boltzmann factor should be a positive real number because it's used as a probability that generates configuration. However, there are many models whose action is not a real number. For instance, in super Yam's quantum mechanics, the integrating fermions provides this coefficient. And this part is not a real number, but it can be negative. So it's not easy to apply this Monte Carlo method to study this model. This problem is called the negative sign problem. And actually, there are many models, many theories with the sign problem.
So Daisuke,
Sorry.
could we simply call it sign problem? Why negative sign problem?
Yeah, it's you can drop this this word, but sign problem is yeah, it's okay. You can drop this.
But if it's a positive sign, usually it's not a problem. So
yeah.
maybe it's
So as you know, the finite density QCD has the sign problem, and chiral gauge theory and supersymmetric theories have the sign problem in general because chiral gauge interaction and chiral Yukawa interaction in Suji models provides the imaginary part of the fermion determinant. So they have the sign problem in general, and the theta terms is introduced as IFF tilde in the action in the Euclidean action, so the theta vacuum physics suffers from the sign problem, and also the real-time simulations, the Lorentzian signature is used, so the real-time simulations is not free from the sign problem. So we can say it's important to solve the sign problem for studying these interesting and important theories. And the tensor renormalization group method is free from the sign problem. As I will explain later, in this method, the partition function is expressed as a network of tensors. And starting from this representation, coarse and coarse graining this network, the Partition function can be evaluated by this coarse graining of the tensor network. So this is a kind of a real space renormalization group method, and this procedure does not have any stochastic process. So it's free from the sign problem from the beginning. Okay, so I don't so I don't have time to introduce many previous studies, but now many researchers are using tensor network methods and tensor renormalization group method to study field theory. Okay. And in this talk, I will be explaining what the TRG method is in two-dimensional Ising model. Then I will apply this method to study complex scalar field theory at finite density. And the cost of TRG strongly depends on the dimensionality. So then I will propose a new tensor renormalization group method to reduce the computational cost. And I called our new method the triad TRG method. And I will show the numerical test result of this method in three-dimensional Ising model. Then finally, I summarize my talk. Okay. And the tensor renormalization group method was originally proposed in condensed matter physics in two-dimensional Ising model. And this is the Hamiltonian of two-dimensional Ising model. And sigma n is a spin variable that takes plus 1 or minus 1. And n is integer lattice type. And the partition function is given as a standard manner, given in the standard manner, and we can show that this partition function is expressed as a tensor network. So before seeing the derivation of tensor network representation, let us introduce graphical representation of tensor networks. This T, I, J, K, L are rank 4 tensor. And in this graphical representation, these 4 indices are expressed as these 4 links. Okay? And the contraction of 2 tensors is given by this figure. And T is rank 4 tensor and S is a rank 3 tensor. And this index K is contracted, and the contracted index K is shown as a shared index. Then K is shared by 2 tensor T and S, and shared index is always contracted in this figure. Okay, and the tensor network of 3 tensor T, S, and R is given by this figure. In this figure, all links are shared by 2 tensors. So all the indices are contracted. Okay. So this is a graphical representation of tensor.
Can I ask a question about the contraction of tensor? Here for the first for the summation T K A B C,
okay.
the sense of notation is anti-clockwise. So
depends on the notation. So yeah, it depends on the notation. So I
didn't understand it.
So actually in the square lattice, the clockwise or clockwise Okay. It depends on the notation. It's possible to label the index. The index. There is many methods. There is many ways to.
Okay. Got it. Thank you.
It's depends
Thank
on
you.
notation.
So do you assume that the tensor T is symmetric here?
It's not assumed here. But normally in two-dimensional Ising model, tensor T is totally symmetric one. Totally symmetric
Okay.
under the interchange of IJ, KL.
So as far as the rest of the talk is concerned, this is symmetric, right? As far as the rest of your talk is concerned.
Yes, in two-dimensional Ising model, it's yes. So, and okay, and the tensor network representation of the Parsing function is obtained by decomposing the hopping terms. And this is the hopping term of the Ising model, and it's equal to hyperbolic cosine term plus hyperbolic sine term. And introducing this new index I, the first line can be expressed as the second line. And I equal to 0. Here is 0. The first term is given, and I equals 1. The second term is given for I equal 1. And by using this 2 by 2 matrix W, this second line can be expressed as 2 W's. In this form, spin variables sigma n and sigma n minus 1 hat are decomposed into 2 W's. Okay. So, the spin variables are decomposed into 2 W's. So graphically, the link hopping terms are originally defined on the link. And after the decomposition, spin variables are two spin variables are separated into the two sides, and the new index I appear here. Okay, and this index I becomes the index of tensor. And by applying this decomposition to all the hopping terms, the Parsing function is given by a product of W. And in this form, we can take the summation over each spin variable because spin variables are separated into W. So we can take the summation over the spin variable firstly. Then tensor T IJKL is defined like this. By using this tensor, the Parsing function is expressed as a tensor.
Daisuke, one question.
Sorry?
On the previous slide,
Previous, right? Okay.
so sigma power I, what does that mean? So sigma power 0, there will be sigma power 0 and sigma power 1, right?
Sigma here?
Yeah, what is the meaning of that? Sigma power I.
Sigma to 0 is sigma is 0 is 1. Sorry, it's 1. And sigma to 1 is plus 1 or minus 1.
It's not the power. It's not the power, but it's index of a Pauli matrix. And sigma 0 is identity. You mean.
Yes, sigma to 0.
And sigma 1 is sigma x, I suppose.
Sigma, yes. Yes.
Okay.
Yes.
And
So-
what is this I in a square root tangent hyperbolic beta j and then I on the
I
upper right?
it's
Oh,
just
go down, down, down,
Right.
go down. Oh, power I. Okay. Tangent to
Power I, yeah,
hyperbolic
power
beta j to the I over 2. This is the definition of W sigma I.
Yes.
Okay. That
W.
is actually power.
Yes. Yes. So
Okay.
yeah. So I runs from 0 to 1. So this W is 2 by 2. So initially, this tensor 2 by 2 by 2 by 2 tensor, because IJKL runs from 1, 0 to 1, 2 by 2 by 2 by 2 tensor. And by using this tensor, rank 4 tensor, the Gaussian function of two-dimensional Ising model is expressed as a tensor network. Because this I, new index I, is shared by two W's. Okay, so this index I is shared by two tensor T's, two tensors. So this is a tensor network like this. Okay. So the Gaussian function of two-dimensional Ising model is expressed as a tensor network. So, and normally lattice field theory with translational invariance provides a locally connected and homogeneous tensor network. Because lattice field theory has translation invariance, and so all the tensor are the same tensor T from the translational invariance. And the locality of lattice field theory means T is connected, locally connected to the tensors, nearest neighbor tensor. So the Gaussian function is expressed as a tensor network. Once tensor network representation is obtained, we can apply the tensor renormalization group method to evaluate this network. And singular value decomposition is used to formulate tensor renormalization group method. And this is the normal singular value decomposition of a matrix T. And for any matrix T, T can be expressed as this form. This is called the singular value decomposition. And U and V are unitary matrices, and sigma M are singular values, and which are sorted in the descending order in this talk. So by using these S and S prime, this decomposition is expressed as this form. Okay. Graphically, the matrix T is decomposed into two S, and new index M, this M, appears between all indices I and J. And by using this singular value decomposition, we can give the low rank approximation of a matrix, of the matrix T, by truncating the summation, this summation up to D cut. Okay. So this is the low rank approximation of the original matrix T, because this approximation is a good approximation because the smallest singular values are dropped in this approximation. So the largest singular values are included in this form. So this provides a good approximation of best D-cut rank approximation of the matrix T. Okay,
So,
and by
guys, one question.
Okay.
For a given system, what determines the size of N, the size of the matrix?
depends on the case. So I will show it in the next page.
Oh, okay.
Okay. Okay. And by using this singular value decomposition, the tensor, rank 4 tensor is also decomposed into two tensors because we can identify these two indices ij as a single index I, and identifying these two indices kl as a single index j. Then this rank 4 tensor is just a matrix Tij. So we can apply this singular value decomposition to rank 4 tensor. So rank 4 tensor is decomposed into this form, like this. Okay. So
But you, so now you say the IJ and the KL are regarded as one.
one index.
So for example, if you have 3 indices, I don't know, 5 indices, and then to try to separate 3 and 2, then it doesn't necessarily work.
Yeah, in this case, all the tensor are given as rank 4 tensor.
In this case, okay, yeah.
Yeah, lattice.
But okay, yeah, I just asked as a generic tensor problem.
Generic net.
So
Maybe
the rank
it's
of
minor, but
yeah, I think the rank of T is determined by the number of dimensions. So it's always 2 times the number of dimension. So in 2 dimensions, it's 4.
Yeah, in square, hypercube.
Okay.
4 x. So it's
Hypercube,
never,
right? Yes, and so this n is in this case 4 because the initial size, initial bond dimension is 2 by 2 by 2 by 2 in 2-dimensional Ising model. So m runs from 1 to 4. Okay, initially 1 to 4. Okay, so and this there is this new index m, it appears between ij and kl, and there is another decomposition. There's another decomposition like this. In this case, new index m appears between il and jk, and this decomposition is applied for tensors on even sides of 2-dimensional sphere lattice, and this decomposition is applied to tensors on odd sides. Okay, so starting from this square lattice network, blue points are even side, and yellow points are odd side. The even side tensors are decomposed into 2 tensors, rank 3 tensors, like this. And odd side tensors are decomposed into 2 rank 3 tensors, like this. Okay, and these dotted lines are new index m, and these dotted lines become the index of renormalized tensor. And by taking the contraction of the old indices, the renormalized tensor is defined from these 4 S's, like this. So the most important point here is that the tensor T is decomposed into 2 rank tensors. But on the other hand, the renormalized tensor is made of 4 S's. So this shows the one-step renormalization, and so the number of tensor decreases after one-step renormalization. Okay, because T is decomposed into 2 S's. the T prime is made of 4s. So this is, and repeating this renormalization again and again, the number, finally, the partition function is expressed as a single tensor T, whose indices are contracted in it. Okay. So we can evaluate this contraction numerically and obtain.
So here, the shape of the lattice was really important. Otherwise, after doing this kind of contraction, shape of the lattice cannot maybe. In this case, after 2 steps, it comes back to the same.
Yeah, it comes back to this form.
Uh-huh.
If 5 degrees rotated.
Like if you started with a triangular lattice, it could be more complicated story.
Triangular, it's not complicated. It's
okay.
possible to formulate.
Yeah, I just wondered if you are using anything special about this lattice, but maybe not.
It's also possible to formulate the TRG in triangular lattice and square lattice, but I'm not sure it's possible to formulate TRG.
Okay, probably it was not the important question. Sorry about that. Thank you.
So, Daisuke, one question. It's regarding the boundaries of the lattice.
Sorry?
So the boundaries of the lattice, is the lattice a torus in the two-dimensional case?
Actually, in tensor renormalization group method, many time renormalizations are carried out. T converges to fixed point tensor. In that case, the size of the lattice is infinity. Okay.
Probably the same tensor is sitting at any point. Also after contraction again, the same one is distributed uniformly. So probably he didn't have to specify the lattice size.
So Anosh, most of these tensor formulations have periodic boundary conditions. People don't know how to do finite temperature yet.
We can use periodic boundary conditions.
Yeah, so most of these are periodic boundary conditions.
Periodic boundary conditions.
Talking about.
So that means it's a torus in 2D.
Yeah. That's a torus. It's in on 2D. It's a periodic boundary condition with the torus. You can also do open boundary conditions if you want, but I don't know of ways of doing anti-periodic boundary conditions yet.
So what you're saying is for actual numerical calculation, you have to specify.
I used the periodic boundary condition, so I've never tried the open boundary condition. So I'm not sure for the case of open boundary.
So periodic boundary conditions just means that when you take a lot of T's together to construct the partition function, you sum over the first and the fourth index. If you sum over the first and the fourth index, it bemes a periodic boundary condition.
Yes,
right? Because you're identifying the first like opposite sides indices. So that's
it's an anti-periodic boundary condition. So but I'm not sure for the case of open boundary condition, but we can assume a periodic boundary condition and anti-periodic boundary condition in this formulation. I'm not sure how to apply this method to open boundary case.
But in open boundary case, it's not translational invariant. So can we do that? Really?
Yeah, I don't know how to do this method in open boundary. I have just worked in periodic boundary conditions.
Okay, so is there any question? Okay. Any other question? Okay. So finally, the partition function is given by a single tensor T. So we can evaluate this contraction numerically, and we obtain the value of partition function. So this shows the magnetization which is obtained by the tensor renormalization group method. Y-axis is the magnetization, the x-axis is a coupling constant.
Let's get one question on the previous slide. So here we can directly compute the partition function. So So does that mean, say, we can compute Witten index? Is that easy to compute Witten index in supersymmetric theories?
Yes, it's possible. We can evaluate Witten index directly by using TRG method.
Yeah.
So, and in the case of magnetization, the external field is included in the action, and applying numerical differentiation with respect to the external field, then the magnetization is easily obtained from the TRG results. And the critical point is 0. And this curve, two-dimensional Ising model is an exactly solvable model. So this curve is exact solution of the magnetization. And these dotted curves are TRG results. Okay, this curve is a result for D equals 4. And this is the result for D equals 10. This is 16, 22, and 28, and 34. So as D cut increases, numerical TRG result smoothly approach the apart from the critical point. Okay, so we can say that TRG properly works in this case.
There's one question, it seems.
Yes, sir. So in this plot for the Ising model, is the external field perturbative or is it 0?
Sorry,
so you have plotted magnetization plot for Ising model. I'm asking, is the external field perturbative or is the external field 0?
Sorry, I cannot hear you, but please speak in loud voice.
Is the external field in this Ising model perturbative or is it 0?
Sorry.
External field. Have you introduced non-zero external field or not?
The external field is set to 0 after numerical differentiation. And so
I guess maybe the related question is, if the external field is 0 and your system size is finite, then you should get exactly 0. So there is some breaking of the symmetry.
Yes. So, but in this case,
but this is not a finite system. This is, I think,
the tensor approaches to the fixed point tensor. In that case, basically it's the result of infinite volume lattice. So infinite volume limit is taken in this figure before setting the external field to 0.
Okay, so each finite system is calculated with a small external field, and then you take L to.
Anytime renormalization zones are carried out, tensor approaches to the fixed point tensor. The fixed point tensor means the result of infinite volume lattice. So infinite volume result is obtained.
So can you go back one slide? One slide back, and so you said fixed point. So D cut is on the lower left. But so this T tilde is for this T tilde you are using this a fixed point tensor.
Yeah, many times renormalization.
It's related to Schaich question. So I want that. So first, the tensor is always 4x4. Fixed point tensor is 4x4.
No.
No.
So,
can I please?
Increases.
Go ahead.
Initially, tensor is 2 by 2 by 2 by 2 here. But after one-time renormalization, renormalized tensor is 4 by 4 by 4 by 4. Because here M runs from 1 to 4. So, and at the bond dimension of the next step, 4 squared, so 16 by 16 by 16 by 16 tensor appears. So bond dimension increases after renormalization, and D-cut is used to stop the increase of the bond dimension. Okay. So up to so for the first few steps, the truncation does not work. For example, if we use D-cut equal to 64, the bond dimension is tensor is smaller than 64 for first few steps, but the bond dimension increases after renormalization, so it works for few steps renormalization after few steps renormalization. Okay, so
I would like to say something.
Yeah,
hello?
Go ahead.
Yeah, as per my knowledge, the tensor renormalization group method that you are describing is basically for a 2D Ising model. The tensor has been constructed a 4-dimensional tensor, but the graph that you are showing is basically for us it's a triangular lattice Ising model. The graph for the magnetization lattice, the 11 and 8 paper that you are showing, it is a triangular lattice magnetization.
This is a result of actually a triangular lattice. Yeah, but that's the similar result is obtained for the square lattice.
And yes, as we if we include the external magnetic field H, then I think the results would become much more like comparable to the exact results, as per my knowledge, I think. But I guess you are not considering the external magnetic field in this particular case, right? For the graph that you are explaining.
Sorry,
I think you are not considering the external magnetic field for the graph in the next slide. I just want to have a knowledge for that. Yeah, this is the 11 and 8 paper. This is for the triangular lattice, and we are not considering the external magnetic field for this magnetization. Is it true?
What do you mean? What is your question?
So I'm just asking about the external magnetic field in this Ising model, the triangular Ising model that you're considering. Have we considered the external magnetic field as well?
I guess when you say consider, I assume you're asking, has he introduced, or is the external magnetic field non-zero?
Yes.
Yeah, the word consider maybe is confusing here.
Sorry.
External field is introduced to perform numerical differentiation. So actually it's set to 0 after numerical differentiation. So this is the result of for 0 external field.
Okay, thank you.
So, okay. So let us summarize the property of TRG, and there is no sign problem, and there is no stochastic error because it does not have any stochastic interpretation of Boltzmann factor, and the error.
Daisuke, one naive question. What is the connection between sign problem and stochastic method?
Ah,
or, yeah. What is
very easy because the sign problem is a problem of the Monte Carlo method. In the Monte Carlo method, the Boltzmann factor is a probability that generates the configuration.
I see. So it's a problem of the algorithm. It's not a problem of the theory.
Yeah. So this algorithm does not use stochastic interpretation of Boltzmann factor. This algorithm does not regard the Boltzmann factor as a probability. So there is no sign problem from the beginning. Okay. So and there is no stochastic errors from the beginning. Only error comes from systematic.
I'd like to make a comment here. So I think the sign problem can come back to haunt you if for some reason the D-cut, it's, I think in some sense, hidden in this D-cut approach.
No.
Right?
No, because sign problem is a problem of Monte Carlo method. So
no, let me try to. You're completely right. So if you can do this without any D-cut, of course you're not doing any approximation. So there is no sign problem.
Yeah.
But in your method, at some point you have to introduce a D-cut. The question is, at the point where you introduce your D-cut, you are asking if your SVD decomposition is able to capture the physics of that low-lying modes, right?
Yeah, yes.
And if typically, I think I completely agree. I think this is a very new and interesting method to think about and see. Maybe for almost all interesting problems, maybe D-cut is, if it is sufficiently large, maybe you capture the most important physics, and that might be true.
Yes.
But I feel that if at all the problem is hard, the problem will come back in D-cut, because that's exactly the way the sign problems come back in Monte Carlo calculations. If you think about it, you can formulate it in different ways. So if maybe during the discussion session, I can perhaps explain what my belief is. But I believe that it is somewhere in the D-cut.
Okay, I have something to say. I think that D-cut problem is more or like related to the finite size effect in lattice, something like that. But it's not related to sign problem, as per my knowledge.
Maybe
I mean, we can have this discussion at the end.
Maybe we should postpone it to discussion session, maybe. And I also have some comment regarding this. And David Schaich wanted to ask something, I think. David, do you want to?
No, I went ahead and put it in the chat window because it's building on what Schaich was saying about
okay.
When you solve sign problems, they can reappear in different forms that don't necessarily have that direct connection to the sign, but still can obstruct numerical results or make the cost greater. So we'll come back to that at the end as the chair instructed.
Okay, thank you.
Okay, so in this method, the partition function or free energy is directly calculable. And the computational cost scale with logarithm of the volume times D-cut to some power. P is 5 for two-dimensional TRG method, which I explained in the previous slide. And in D dimensions, higher order TRG and anisotropic TRG methods are used to study D-dimensional hypercubic network. For those methods, P is 4D minus 1 and P is 2D plus 1 for ATRG. So the power P strongly depends on the dimensionality. Okay. So the cost of TRG becomes high as dimensionality increases. So okay. So I will apply this TRG method to study two-dimensional complex scalar field theory at finite density. And chemical potential mu is introduced here, and this action has a this theory has a sign problem because the action has pure imaginary part due to the chemical potential. And it's well known that bulk of observables are independent on the chemical potential below some critical value. This is so-called silver bullet phenomenon. No, and the silver bullet phenomena is closely related to the phase of the of this action. So I will check whether the silver bullet phenomena is observed by the TRG or not to test the TRG method. However, in scalar field theory, the scalar field is continuous variables. So we have to discretize of scalar field to define finite dimensional tensor. In Ising model, the tensor T is initially 2 by 2 by 2 by 2 tensor because Ising spin takes +1 or -1. So, however, for scalar fields, the bond dimension naively become infinity. So we have to discretize the scalar field to define finite dimensional things. And for discretization of the scalar field, we used Gaussian coordinate, which is a numerical integration method of one-dimensional integral. And this one-dimensional integral is approximated by a summation over k discretized point. This is a well-known Gaussian quadrature formula. And this sk is a set of roots of k's Hermite polynomial. And gk is a weight function. And for exponentially damping function f, this integral is well approximated by this summation. And this approximation is improved by increasing k. And so this integral is expressed as the summation over the k discretized point. And to discretize the scalar phase, the integration measure of past integral is replaced by this summation. So the scalar field is simply discretized. And after this discretization, the hopping terms of scalar fields.
One small question. So this phi 1, phi 2, etc., they correspond to what? Lattice sites or?
This one is scalar field. Lattice 1, 2, and n levels lattice sites.
So there are n number of sites.
Number of sites.
Okay.
D is needed here. Okay. Number of sites. So all the scalar fields, all the measure of scalar fields are replaced by the summation, just summation over k discretized. So then hopping terms of the lattice model becomes k by k matrix because scalar field phi takes k discretized value. So this hopping term is a k by k matrix. So we can apply singular SVD to this k by k matrix to obtain this form. And by defining this W1 and W2, hopping term is decomposed into 2W as well as done in the Ising model. So tensor T is introduced like this. The Partition function of scalar field is expressed as a tensor network with this tensor. So once tensor is obtained, we can apply TRG method to two-dimensional scalar field theory. And this figure shows the particle number density against chemical potential. So as you can see, for large volume lattices, the number density does not change up to some critical value. So the silver blaze phenomenon is clearly observed by the TRG method. And also the expectation value of phi square is computed by the TRG, and the similar behavior is observed for this expectation value. The clear silver blaze is observed. And the severeness of the sign problem is often measured by the average phase factor. This phase is the phase of the Boltzmann factor, and if this phase takes +1 or -1, average phase factor vanishes. In that case, it means the sign problem is very severe. So as you can see, the average phase factor vanishes for all the chemical potential mu, which we used in the calculation. And here is a critical chemical potential, but for almost all the chemical potential, the average phase factor vanishes for large volume lattices. But the silver blaze is clearly observed. This means that the TRG properly works for the theory with severe sign problem. And this figure shows particle number density, which is obtained dropping the phase part of the action. If the phase part of the action is dropped, the silver blaze phenomena is not observed. And this figure shows the behavior. This green curve is the result of phase quantity theory. Then the silver blaze is not observed. But in full theory, silver blaze is observed. So the silver blaze is closely related to the phase of the theory. And it's clearly observed by the TRG. So TRG is properly works for the theory with severe sign problem. Okay. So in 2 dimensions, TRG effectively works. However,
sorry. Could I ask a question? Mm-hmm. You have both the volume here, but you also have the discretization of the scalar.
Okay. We have to check the convergence.
Yeah.
By changing k, but in this figure we took k is 64, and 64 is large enough to converge the results.
So I guess if you took larger than 64 with the same D cut, you're saying you're not sensitive to increasing k.
For fixed D cut, in this case D cut is 64. Yeah. By changing k, by changing k, this result does not change changing k.
Yeah.
So the finite k effect is saturated for this value of k.
Thank you.
Okay. So in 2 dimensions, TRG properly works for lattice field theory. And in higher dimensions.
So before going to section 3, I want to ask to Anosh. So it's almost an hour, but there are many questions already. So maybe it's okay to so he can continue maybe 15 minutes.
Yeah.
Sure. Okay. Mm-hmm. Yeah, it's until 15 minutes. Okay. You have 15 minutes from now.
15 minutes. Okay. Okay. So in 2 dimensions, the TRG works. So, however, the cost of tensor network methods becomes expensive for higher dimensional theory. For example, the higher order TRG is used in higher dimensional tensor networks, And the renormalization steps of higher order TRG is made of 2 steps. This figure shows a 3-dimensional case, and in the first step, from 2 tensor T, the projector U is created from the 2 tensor T, and in the second step, by using the projector U, 2 indices x1 prime and x2 prime are combined into a single index x prime. In the first step, this M is rank 10 tensor because it's made of 2 T's and 1 index is contracted here. So M is rank 10 tensor. And regarding this tensor as a matrix whose row is x1 and x2 and columns are the other tensor, other indices, then M dagger is d square by d square matrix. So U is a unitary matrix that diagonalizes this dagger. But once the unitary matrix is obtained by using this unitary matrix, and by taking the contraction between U and this M, these 2 indices are unified into 1 index by contracting between U and M. However, this x prime runs from 1 to d squared because U is d squared by d squared matrix. So actually, x prime runs from 1 to d squared. So here, the truncation is used. The x prime is truncated up to d, from 1 to d, by taking eigenvectors of the largest eigenvalues of dagger. So the important information of M is kept after the truncation of this index. So the x1 and x2 are also combined into a single index x, and the same thing applies for the y direction. So these 2 tensors are renormalized into a single renormalized tensor D prime by taking all the contraction in this figure. Okay. So this is a renormalization step of higher order theory method. But the cost of making dagger scale with D to 2D plus 2 and the leading cost of HOTRG comes from this contraction, which scale with D to 4D minus 1. Power is very large, so in 2 dimensions, 4D minus 1 is 7. It's 15 for 4 dimensions. So the difference between 2-dimensional case and 4-dimensional case is very large, D to the 8th. The difference is D to the 8th. So if the computation ends in a few hours in 2 dimensions, for D equals 32, but in the same computation takes the time takes much more time. For example, in 2 dimensions, the computation ends in 90 minutes. For D equals 32, in 4 dimensions, 1.5 hours times 32 to the 8th, because the difference between 4-dimensional case and 2-dimensional case is D to the 8th. So this factor is needed. And this is 200 million years. We cannot wait for such a long time to obtain 4-dimensional results. So we need to create a low-cost renormalization scheme applicable to higher dimensions. However, why the cost of HOTRG is high? This is because the rank of tensor is 2D. in D dimension. In D dimension, tensor T is a 2D rank tensor, and the cost of contracting 2D rank tensor is high as the dimensionality increases. So this is the reason why the cost of HLTRG is high for higher dimensional theory. So to reduce the computational cost, we should reconsider a tensor network theory from a fundamental level. And as you know, the protons are made of 3 quarks. So 3 quarks are the fundamental building block of proton. What is the fundamental building block of rank 6 tensor? It's rank 3 tensor. The rank 6 tensor is made of 4 rank 3 tensors. This is a 4 rank 3 tensors, and these dotted lines are internal index. By taking contraction of these internal lines, this network becomes rank 6 tensor. So rank 3 tensors are fundamental building block of rank 6 tensor, rank 2D tensor. I called this structure triad in this talk. Okay, and this triad structure is hidden in this definition of tensor, which is obtained from lattice action. As we saw in the previous slide, that rank 4 tensor is given as a product of 4W, and in 3 dimensions, rank 6 tensor is given as a 6W for any lattice model with nearest neighbor interaction. Each W comes from the hopping term of the lattice action. Normally, by taking this summation, we use rank 6 tensor in higher order TRG calculations, but without taking this summation first, we can define rank 6 tensors A, B, C, D, like from these W's. Rank tensor is expressed as a tensor network of rank 3 tensors. So triad structure is hidden in this form. And instead of using this rank 6 tensor, we can use this form to formulate tensor renormalization group method. Okay. So this triad structure is not unique. The representation of triad is not unique.
If you just count the number of legs, any tensor can be decomposed by 3 tensors, right? So does it work in general, even if you have more?
In general, okay. More naturally, the lattice model provides this form. This form.
Okay. Okay.
And so the triad representation is not unique. There are many kinds of triad representation. So in this talk, I will use this representation to formulate the tensor renormalization group method. And by replacing rank 6 tensor with triad representation, hypercubic tensor network is naturally expressed as a triad network, which is made only of rank 3 tensors. And the cost of RG on a triad network is naturally reduced because all the tensors are the rank 3 tensors. And the cost of contracting rank 3 tensors is not expensive. For example, in this case, these figures are made only of rank 3 tensors. By taking the contraction of these dotted line, the rank 4 tensor or rank 3 tensor are obtained from these figures. But the cost of contracting these internal lines takes d to the fifth. This is because all the tensor are given are the rank 3 tensors. So the cost of taking the contraction is not expensive for rank 3 tensors.
Can you comment on the rotational symmetry as a function of d?
Rotational symmetry of the
because the tensor seems to have lost the rotational symmetry that you really want. So the question is whether it is somehow encoded in the size of d.
Sorry.
But it's just a mathematical realignment, right? So it does not spoil the rotational symmetry. So it's exactly realignment, I thought.
No, yes. But if you don't cut your dimension, I agree with you. But at some point you're going to cut the way you're going to do your cutting, right? That's important, isn't that true?
Okay, I understand your point.
In this figure, all the tensors are 3 tensors, and the bond dimension is d. So taking this contraction is not the cost of taking the contraction is not expensive. Okay,
it's not okay. The cost. I'm talking about the symmetry of the problem.
It's not related to the symmetry. It's not related to the symmetry. Just the
maybe he wants to know. Schaich wants to know how big d is needed in order to have a good restoration of restoration symmetry. I guess is it your question?
Yes, that's right. So as you do your RG blocking, how much?
Hypercubic lattice.
Yeah, as you do your RG blocking, right? How much is the D cut necessary to keep your rotational symmetry as you grow?
There's no relation between the geometry of the lattice
and symmetry is restored as D cut increases. Yes.
So Schaich, the thing is that once you make your initial tensor, that is the T you start with. So you start with, say, some T, like the T for two-dimensional Ising model is 2 to the 4. So you start with that T and you coarse grain that T, and that keeps the shape of the lattice. So if you start with a T which is defined on a square lattice, once you finish your coarse graining process, you will still end up with a square lattice.
T is fixed.
So there is no relation between the geometry of the lattice and this D, which is D cut. So this D is the same as D cut
by hand. D is fixed by hand.
It's
throughout the computation.
Yeah, so if you can prove to me that the symmetry of the lattice comes out after 2 times 2 RG, then I'll agree with you. I think what I'm worried about is that the way you're writing that symmetric tensor originally into a product of many tensors, that is an exact relation if you keep all the terms.
Yes, I agree.
But then if you start cutting things, then I don't know how the symmetry propagates. That's all. I'm not talking about geometry. I'm talking about symmetry.
Yeah, that's true. But I think the D is more related. So for example, if you are sitting at a second order critical point, then in principle, the D should be very large. You should have an infinite D to reproduce the critical properties.
Yes.
But if you have a gapped system, for example, then you can do with finite values of D, still reproducing the shape of the lattice and get the, for example, the thermodynamic properties like free energy, magnetization, and so on. So that is my understanding. Yeah, but there's no proof. It's just what we see in the simulations. So yeah, I cannot prove it to you that.
I think that we are enjoying a lot. It's a really good thing, but at the same time, we have to let Daisuke finish the talk. So maybe please go ahead.
By using this triad representation of tensor, we apply the higher order TRG like renormalization step to triad network, and M dagger is given in this form in the triad representation. In triad representation, M is given as a network of rank 3 tensors, and M dagger is a mirror image of M, and so M dagger is given by this network, and all the tensors are made of rank 3 tensors, so we can evaluate dagger in the by d in the d to the 6 cost. And once dagger is obtained by diagonalizing dagger, the projector is obtained. And projector U can be exactly prepared and at an order d to the 6 cost in any dimension. The cost does not depend on the dimensionality in the triad representation. This is completely different from the hypercubic higher order TRG on the hypercubic lattice network. So in that case, the cost of making dagger scale with d to the 2d plus 2, but in the triad representation, the cost of making dagger does not depend on the dimensionality. And d to the 6 cost is reduced to d to the 5th using the randomized SVD technique. Which is some numerical technique of the singularity condition. And once projector U's are obtained by using projectors, 2 triads are renormalized into a single renormalized triad by contracting 2 tensors, 2 triads, and projectors. And the cost of renormalization step scale with d to d plus 3 in this case, and starting from 2 triads and contracting between 2 triads and projectors, we can take contraction of this figure and obtain this network in this cost. And this is rank 5 tensor. This is rank 6 tensor. Sorry, rank 4 tensor, and this is rank 5 tensor. And this part, this rank 5 tensor is decomposed into this form by using randomized SVD technique. And this part is also a rank 5 tensor, which is decomposed into this form by using randomized SVD. And finally, this rank 4 tensor is decomposed into this form. So the theoretical cost. This table shows the summary of theoretical cost. The cost of TRG is d to the 5th in 2 dimensions, and the cost of HOTRG and anisotropic TRG methods are d to 4d minus 1 and d to 2d plus 1 respectively. However, the cost of triad TRG method is drastically reduced to d to d plus 3. So the cost of 4-dimensional theory is the same as that of 2-dimensional HOTRG method. Okay, so we will test this new triad TRG method in 3-dimensional Ising model in this case. So this figure shows the numerical test results of triad TRG method, and the theoretical d-dependence is properly reproduced in the actual computations. The triad TRG the computational time of triad TRG scale with d to the 6 in this figure. And this figure shows the free energy against d cut. As you can see, the triad TRG method shows good convergence as d increases. And the maximal d cuts are different among these 3 methods because the computational time strongly depends on the d cut. All the points are obtained for a few hour calculations using laptop computers. And this figure shows the free energy against computational time. This figure says that the trial TRG method nicely reproduces the converged value for this range of time. However, the other methods need much more time to approach a converged value around minus 3.509. Okay, so naively we evaluated the time that ATRG method reproduces this value. It needs 300 years to reproduce this line. So I think the new method is very effective in at least in 3 dimensions. So finally, I summarize. So TRG method, the good point of TRG method is it does not have sign problem, and it does not have statistical error. The free energy is directly calculable, and large volume limit is easily taken. And the bad point of TRG is the cost of TRG is expensive for higher dimensional theory and for theories with large internal degrees of freedom. And we found that Gaussian quadrature works to scalar field theory to define finite dimensional tensor. And triad networks are effective in higher dimensions, at least in 3 dimensions, to reduce the computational cost. And we have already tested 4-dimensional complex, computed the whole dimensional complex scalar field theory at finite density using the tensor anisotropic tensor renormalization method, and silver braid phenomena is almost observed in this case. So this is the result using ADRG and the parallel computation of ADRG on a supercomputer. So the error, I think the error will be reduced by using the triad TRG method. I'm making a simulation code of triad TRG method for 4-dimensional theory now. And I didn't explain the fermionic, the TRG method to fermionic theory in this talk, but the Wiseman TRG method is used to fermionic theory, and this method is reformulated in this paper in much more clear form. And also TRG method is also applicable to lattice gauge theory by using character expansion of gauge group to define a tensor network. And actually, there are many kinds of triad representations, so it means there are many variants of triad TRGs. So I am now looking for the best triad representations to find the best triad TRG method. And the most difficult problem of this method is that the computational cost is high for theories with large internal degrees of freedom, such as large and gauge theories. I think to solve this problem, the quantum computer is needed to solve this problem. Okay, thank you.
Thank you very much. So we have 8 minutes for questions. Do you have any? Does anybody have a question? So Raghav, oh, you're just okay, not raising hand. So any question or comment?
What about the time of calculation combining for fermions and the scalars? It is more or it's the same thing approximately?
Oh, time of sorry.
So fermion and bosons, if so cost for fermion and cost for boson, that was a question, I think.
Okay.
Yes,
The
it is.
cost depends on E cut. So so it's controlled by D cut. So it's not related to the fermionic theory or ozonic theory. So, but I think for theories with large internal degrees of freedom, we have to use larger D cut to renormalize large internal degrees of freedom. In that case, the cost becomes expensive for the theory with large degrees of internal degrees of freedom. Okay, so
So the fermion equals to large degrees freedom, right?
For example, large NGL model, the large D cut is needed, I think. So the cost becomes expensive for large NF NGL model. So, however, for fermionic theory, the fermion, the one component fermionic fields, we don't use, the large D cut is not necessary to renormalize single component fermionic theory. I think large NF, for large NF in general, the much larger D cut is needed to renormalize such a theory.
So Jun Nishimura has a question.
Yes, I would like to understand the principle behind using the Gaussian quadrature. Why do you use this particular kind of discretization? What is the reason?
There are many kinds of Gaussian quadrature. For example, Gauss-Hermite quadrature or Gauss-Legendre quadrature or something like that.
Yes.
But the scalar field theory has the exponentially damping factor as a master.
So
I think Gauss-Hermite quadrature is a natural choice to discretize this integrand.
I see.
Declare that this integration.
I see.
Yeah. So.
Yeah. Okay. Thank you.
And
just to add that there are also other methods to discretize a scalar field, which people have explored, apart from this Hermite quadrature thing.
Okay. Thank you.
And Minati is also raising hand.
Yeah. So I'm asking how to choose a particular decoder for a particular theory. I mean, is that only trial and trial method, or I mean, how to choose a decoder for a particular theory?
So,
is it the value of decoder? Is it audible? How to choose the value of decoder for a theory? Is it the way we need to check and decide, or is that the trial and error method, or I mean, my question is clear?
Yeah, your voice is clear.
Yeah. So, how to choose decoder for a particular theory?
Decoder? No.
How to choose the value of decoder?
We have to check the convergence
of the.
Okay, so it's like for different theory, we have to check where that convergence happens for a particular degree. Okay, thanks.
We have to check the convergence of the cut for each theory.
Okay, okay, thank you.
And Anosh?
Toby has a question. Toby is not able to raise his hand. So
I can't find the button. Jun Nishimura gave a nice talk yesterday about the IKKT model, which has no dimension, but has a sign problem.
Yes.
Now, that sign problem is obviously not, maybe a different sign problem. I guess in principle, you could use tensor networks. You would have to discretize using this Gaussian quadrature, the fields you have, and you would have to also treat fermions. But it must be that you recover, I would have thought, a sign problem when you take the large K limit, or you get continuous fields again.
I want to say that the sign problem is the problem of the Monte Carlo method. If we use the other method, there is no sign problem from the beginning.
No, but you may have a problem of convergence.
Convergence.
You have to take various limits, and you may have a problem of convergence. I can't see how you can avoid it in that case.
Convergence for K is not, we have to check the convergence for K by increasing K, but it's not related to the sign problem. It's not related to the sign problem.
I mean, there may be an issue of terminology here where you can have problems with signal to noise ratio, convergence, things like that, that do not come directly from a sign of a Boltzmann factor, but they are different manifestations of the same numerical challenge. And that, I think, is where the discussion is maybe talking past each other, that it's very clear that there is no issues with Boltzmann factors being interpreted as probabilities in this case, but there can still be issues with those exponentially increasing costs that, in the context of bona fide sign problems, would come from that.
To say it another way, in that IKKT model, you just are doing some integrals, but they're oscillating integrals, and that must be difficult to do.
Because the IKKT model does not have the exponentially damping factor.
Maybe Nishimura-san also can make some comment related to his raising hand. Jun, maybe you want to comment something?
Yeah, I was trying very hard to apply TRG to this IKKT model actually myself. But you see, the problem is that, as Daisuke mentioned at the end of his talk, if you have a large internal space, like large N gauge theory, it is very hard to discretize that. So that is basically the problem. And you don't have, translational invariant lattice or anything like that in the IKKT model. So I'm afraid this method is not very useful.
But even if you wanted to simulate it at finite
theory, but it's already used.
So it also has another problem, that all these IKKT BFSs, it's very difficult to implement anything with internal symmetry groups. Say, for example, SO10 or SO9. Those things cannot be done using tensor network methods, to my knowledge. So it's all. So you can, if you have a SUN gauge theory with SO9 symmetry, R symmetry or something, no one knows how to write a tensor network formulation for that, because it's difficult to do internal symmetry groups in tensor networks.
The TRG method is not applicable to IKKT model and BFSS model.
No.
TRG is defined for two-dimensional theory and three-dimensional theories.
But I'm saying that anything with
one dimension.
the question was whether you can do these sort of things for IKKT. That is what I got the impression of, and it's not possible. That's the answer, because TRG is not suited for anything which has something like R-symmetry groups. That's, I think, the short answer.
Actually, now officially discussion time, it almost ends, but maybe many people still want to discuss. So first, close the session now at official level, and then, but still we can continue, I think. And so first, I suggest everybody thank Kadoh, Daisuke Kadoh again. I think in terms of the number of questions, he is so far the best talk in this workshop. He got most, biggest number of questions. So thank you very much. And yeah, and we can still continue. And if anybody has a question, please.
So Daisuke, I wanted to ask something. Have you looked into 3D, for example, say 3D U1 gauge theory with say theta term? Have you thought about doing
2D U1 gauge theory?
Yeah, say 2D U1 gauge theory with theta term using your new method, or say 3D U1 gauge theory with your new method or something like that. Because you can do U1 gauge theory with tensor renormalization group methods, right? So have you explored those theories?
Okay, it's very easy to use TRG to that theory, U1 gauge theory.
No, but in 3D U1 gauge theory with a theta term has no Monte Carlo because of sign problem.
It's possible. It's easy.
Okay.
It's difficult.
Theta term is only exists in 2D and 4D, but not in 3D, I think.
Right. Yeah, theta term. Yeah.
Yeah, but yeah, I was talking about 2D as well. So yeah, 2D U1 plus theta. Anyways, yeah.
Other question or comment or objection? Nishimura-san, are you raising hand still, or you just didn't turn off?
I didn't turn off, sorry. So what is the perspective for using TRG for QCD? Finite density QCD, I mean.
The character expansion is needed to define tensor network for theory. For SU2 case, the character, it's easy to define, use the character expansion. However, for SU3 cases, there are many different representations for SU3. So in principle, it's possible to define the tensor for SU3 case, but actually, I think we have to use the other method to define the tensor for theory. Yeah, I'm thinking of that.
I see.
The method, but yeah, I think it's the another idea is needed for SU3 theory.
I see. Do you have any particular guess? Like, if not character expansion, then do you have any other guess right now?
Character expansion?
I mean, if not character expansion, then what do you think that might be better? Like any Gaussian quadrature or
character expansion is used for it's easy to use character expansion for U1 and SU2 gauge theories. Of course, it's possible to use the character expansion for any SUN gauge theory, but actually, there are many different kinds of representation in SU3 gauge group. So actually, it's difficult to apply character expansion for SU3 gauge theory.
I mean, if not character expansion, then what other possibility can we choose?
For example, numerical integration of Hall measure is it will be used to define a tensor of lattice field.
So now two more people are trying to ask questions. So one in chat window and one person is raising hand. Maybe first go to Arpit Kumar raising hand now.
Thank you for such a nice talk. So I wanted to know, so what all symmetries are intact in the tensor TRG method and what are broken?
Internal symmetry is broken in tensor renormalization group method. So, so but the in the actual computations, that symmetry is restored, taking the sufficient large d-cut. So I don't think that it's the problem of the TRG.
Okay.
So
okay, thank you. Thanks.
Yeah, can I ask another question? Or maybe Vamika along here want to ask the question in the chat. Yeah, I want to ask a question in maybe page 45.
45?
Oh, so sorry, maybe. Yeah, this one. So the dashed line, is that the analytical result?
No, it's this result is obtained by the numerical extrapolation from our result to the infinite d-cut.
There's no exact result for three-dimensional Ising model.
Yes,
I see.
We don't have the exact result. So this is obtained from the numerical extrapolation from our result to the infinite d-cut image.
Yeah, in that case, you are sure that the three method will give the same convergence?
I've never tried to check the convergence, but Akiyama, who is a student of Tsukuba University, tried to check the convergence from the HOTRG. He said this converged value is obtained from HOTRG method by extrapolating HOTRG result to the large d-cut. The same converged value is obtained from HOTRG.
Okay, I see. Thank you.
Akira Matsumoto is raising hand. You can unmute and speak.
Yes. So I have a question. So if you want to simulate something like full QCD, which have both of the boson and fermion, is it possible to apply TRG method to such a theory?
Boson means
I mean gauge field and fermion field.
Yeah, it's possible to apply the TRG to the QCD.
In that case, the tensor have tensor have both of bosonic variable, bosonic indices and fermionic indices.
Yes.
I see. So, okay, I understand. But in that case, how to treat d-cut is both indices are combined, or we need to treat
it's a good
bosonic
question.
indices and fermionic indices separately.
It's a good question. In the previous studies, the combined index is used to,
I see.
To treat the fermion Physics theory with scalar field. So combined index is used.
Okay. Yeah, thank you. Yeah.
Other question, comments, objection? If not, maybe finally Daisuke can be free. No. Thank you very much.
Thank you.